In this video, we're going to solve a kinematics problem. This is an interesting problem where we see two types of motion. So here we have a collar at point C. It could be something on a manufacturing line, for example, and it slides with a linear velocity and acceleration as shown here. So the velocity c is 2 meters per second to the right, and the acceleration at point C on the collar is 10 meters per second squared to the left. The collar is attached to link BC through a pin joint at point C. So we're given the length of BC and the length of link BA. So what we're asked to find here is that at this instant, we're asked to find what is the angular velocity of link BC and the angular acceleration of link BC. I like to write down what we're given. So here we're given VC, the velocity of the collar, and so I'm using my standard coordinate system. So we're told that the velocity at point C is 2 meters per second to the right, so that's 2I hat meters per second, okay? Where I hat is our unit basis vector in the x direction. And AC, so we're told that it's 10 meters per second to 10 meters per second squared to the left, so that's negative 10I meters per second squared. All right, so when solving kinematics problems, the first thing to do is to figure out what kinds of motions we're experiencing. So we can see here that at point C, it's undergoing translation along with the collar. Point B is attached to both link BC and link BA. We notice that link BA is undergoing fixed axis rotation. So this is at point A, we have a fixed point here attached and to with a pin joint to link BA. So we can write here AB is fixed axis rotation. But BC is a bit more complicated because we can see that point B can rotate about point C, but point C can also translate. So it's not a fixed point. So what we have with BC is general planar motion. All right. So for general planar motion, what we can do is let's express the velocity of point B on link BC. Okay, so we have the velocity of point C is equal to the velocity of point B plus the relative velocity of point C with respect to B. So at this point in time, VB is an unknown. We don't know what VB is. We know that the relative velocity of C with respect to B mimics fixed axis rotation. So we're going to have omega BC crossed with R of C with respect to B. Similarly, for the acceleration at point C, for general planar motion, we have the acceleration at point B plus the relative acceleration of C with respect to B. And so recall that the relative acceleration has two components. We have a tangential acceleration component and a normal acceleration. So alpha BC crossed with R of C with respect to B. This is the tangential component. And the normal component will be minus omega squared BC multiplied by R of C with respect to B. Okay, so VC and AC are given in the problem. We're asked to find omega BC and alpha BC, which appear over here. We know the geometries, but we don't know AB, and we don't know VB. So these were equations for link BC. Let's have a look at link AB. So as mentioned, link AB undergoes fixed axis rotation. So let's come up with an expression for the velocity of point B for fixed axis rotation. And it's just omega AB crossed with R of B with respect to A. So at this point, we don't know what omega AB is. We're going to assume that omega AB is in the positive k direction. So if you recall, so positive for I is to the right, positive in the j hat direction is up, and k is positive counterclockwise. So this is just an assumption at this point, since we don't know, we actually don't know omega AB. Now R of B with respect to A will come from the geometry. So we have the link length, which is 0.6 meters, and we have the angle between the link and the horizontal of 60 degrees. So we can say that it is 0.6 cosine of 60. And note, R of B with respect to A is going from A to B. So for us to go from A to B, we need to go in the negative I direction. And to go from A to B, we also need to go in the positive J direction. And that is 0.6 sine of 60 in the J direction. Okay, we can simplify this a bit. Let's just evaluate these cosines and sine terms, and then we're going to carry out the cross product. So this is minus 0.3 in the I direction. And this is 0.52 in the J direction. Okay, so now we need to take the cross product of omega AB in the K direction crossed with negative 0.3 in the I direction and 0.52 J in the J direction. You might remember from high school how to take cross products. And this is your positive direction. So if you take I crossed with J, you'll get a K. If you take K crossed with I, you'll get a J. Now, if you go in the opposite direction, K crossed with J, you'll get an I, for example. So here we have K crossed with I. So that should give us a positive J, but we have the negative sign inside the bracket over here. So we'll be in the negative J direction. So we'll have minus 0.3 omega AB in the J direction. Then we have K crossed with J. So K crossed with J will give us a negative I. So we have negative 0.52 omega AB in the I direction. Okay, so we're going to call this equation 1. All right, we're going to use equation 1 in our expression for equation 2, VC. And we're going to substitute this. So if we write 1 into 2, we have VC is equal to VB, and we found VB to be negative 0.52 omega AB in the I direction minus 0.3 omega AB in the J direction plus, and now we have omega BC crossed with R of C with respect to B. So as we did with omega AB, we're going to assume a direction for omega BC. So we have omega BC in the K direction crossed with R of C with respect to B. So to go from B to C, we go 0.4 cosine of 45 degrees in the I direction plus 0.4 sine of 45 in the J direction. Okay, so let's carry out this cross product over here and also carry out the multiplication of 0.4 cosine of 45. So we have 0.52 omega AB in the I direction minus 0.3 omega AB in the J direction. Now again, we're going to use our little triangle over here to help us with our cross products. So K crossed with I gives us a positive J, and K crossed with J will give us a negative I. So first we have a negative, and 0.4 sine of 45, if you carry out the multiplication, that's just roughly 2.283 omega BC in the I direction. And then K crossed with I gives us J, and it's a positive J. And 0.4 cosine of 45 is also 0.283 omega BC, and that is in the J direction. So now what we're going to do, we're going to group terms that are in the I direction and group the terms that are in the J direction together. So we have minus 0.52 omega AB minus 0.283 omega BC, and these two are in the I direction, plus 0.283 omega BC minus 0.3 omega AB in the J direction. Now note that we know what the velocity at point C is. So the velocity at point C is 2I meters per second. It is undergoing translation in the I direction, and there is no J component. So if we want, we can write it and be very explicit about it and write 2i plus 0j. And the reason I did this is that embedded in this vector equation are two scalar equations, one in the I direction and one in the j direction. So if we equate the I terms to get on the left and the right hand sides, and the j terms on the left and right hand side, we're going to have two equations for two unknowns. So let's go ahead and do that. So if we equate the I terms, we have 2 is equal to minus 0.52 omega AB minus 0.283 omega BC. And equating the j terms, so on the left-hand side we have 0. On the right-hand side, we have negative 0.3 omega AB plus 0.283 omega BC. Two equations, two unknowns. If you solve for these two, you will find that omega AB is equal to minus 2.44 radians per second. And omega BC is equal to minus 2.59 radians per second. Now let's think about this for a second. We have negative 2.44 and negative 2.59. What this means is that our assumed direction for omega AB and omega BC, so that was assumed to be in the positive k direction, is actually incorrect. And the angular velocities are in the clockwise direction. So we can write that omega AB is equal to negative 2.44 k radians per second. And omega BC is equal to negative 2.59 in the k direction radians per second. Okay. So these are both in the clockwise direction. Okay, so recall that we were asked for omega BC and alpha BC. So we have our first answer, omega BC. We're going to use the same procedure to find alpha BC. So up here, which I'll call equation 3, we have a relationship between AC and AB. Now, we have several unknowns. We are given AC in the problem, but we don't know AB, and we don't know alpha BC. We just found omega BC, so that helps. So we need another relationship for the acceleration of point B. And so what we're going to do is look at link AB again. So for link AB, it is undergoing fixed axis rotation. So for fixed axis rotation, we have a tangential component of acceleration, and a normal component of acceleration. So as we did before, we're going to assume a direction for alpha AB. We're going to say, let's assume it's in the positive k direction. And r of b with respect to A means that we're going from A to B, that is the position vector, so that's negative 0.3 in the I direction, plus 0.52 in the j direction. Minus omega AB squared. We know what omega AB is from the previous step. but let's just leave it as a variable for now. And again, we have negative 0.3i plus 0.52j. Okay, so we need to carry out our cross product. Well, in the second bracket, it's just a straight up multiplication. So I'll draw this out again here. This is our positive direction. So we have k crossed with I, that'll give us a positive j, but then we have the negative over here. And we have k crossed with j, which will give us a negative I. So we have negative 0.52 alpha AB in the I direction. And then k crossed with I is j, and so we have a negative 0.3 alpha AB in the j direction. Plus 0.3 omega AB squared in the I direction minus 0.52 omega AB squared in the j direction. So we can actually find numerical values for these two terms here because we have omega AB, we know it to be 2.44. So what we're going to do is that we're going to group I and j terms together. So this gives us 1.786 minus 0.52 alpha AB in the I direction plus negative 3.096 minus 0.3 alpha AB in the j direction. And we're going to use this expression to substitute into equation 3. So if we call this one equation 4, we're going to put 4 into 3. So we have AC is equal to AB plus the relative acceleration of C with respect to B. So AB is taken from equation 4. So that's just 1.786 minus 0.52 alpha AB in the I direction minus 3.096 minus 0.3 alpha AB in the j direction plus, and now we're going to have that relative acceleration of C with respect to B. So we have the tangential component, alpha BC, assumed in the positive k direction, crossed with the position vector of C with respect to B. So recall the position vector, C with respect to B. We're going to go 0.4 cosine 45 to the right and 0.4 sine 45 upwards. So this is 0.283 in the I direction plus 0.283 in the j direction. Finally, we have the normal component, which is omega BC squared, which we've solved for in the previous step. That is 2.59 squared. multiplied by r of c with respect to b. So again, 0.283 in the I direction plus 0.283 in the j direction. In addition, we know what AC is. We are given that AC is equal to 10 meters per second squared to the left. So it has a velocity to the right and an acceleration to the left. So it is decelerating, essentially. So we can replace this with negative 10I. And then we'll group I and j terms together and carry out our cross products over here and carry out our multiplications over here. And I will give you the intermediate result. So we have negative 0.112 minus 0.52 alpha AB minus 0.283 alpha BC in the I direction plus minus 4.994 minus 0.3 alpha AB plus 0.283 alpha BC. All of this in the j direction. So again, in this vector equation is embedded two scalar equations, one for the I direction, one for the j direction. So the left-hand side could be written as negative 10I plus 0j. So we can write two equations. Minus 10 is equal to minus 0.112 minus 0.52 alpha AB minus 0.283 alpha BC. And in the j direction, we have 0 on the left-hand side. On the right-hand side, negative 4.994 minus 0.3 alpha AB plus 0.283 alpha BC. And here we have two equations for two unknowns. Solving the equations gives us alpha AB is equal to 5.97 radians per second squared, and alpha BC is equal to 24 radians per second squared. So both of these came out positive, which means that our assumed direction, so up here we've assumed that alpha BC is in the positive k direction, that assumed direction is correct. So if we want to express our result in vector form, we would say that alpha BC is equal to 24 k radians per second squared. So this is how we solve typical planar kinematics problems for rigid bodies.